Okay. Hi everyone, and welcome to this special session in which we have Henrique Camara from Instituto Superior Técnico de Lisboa. That is going to talk to us about dark matter models, but high energy physics. So in this seminar, we're going to have a part for gravity and a part for high energy physics people, and that's very nice that we can have this bond now. And hope you enjoy. And please, Henrique, welcome.
Okay, good afternoon, everybody. Well, first of all, I would like to thank the organizers of the GRAB seminar and also the Beyond the Thermal brainstorming meeting for giving me the opportunity to present my work here in the seminar. So I'm actually a PhD student at the Technic, CFTP, and I'm going to present a work that I'm in collaboration with Deborah Barreiros and Philippe Joachim, which is my PhD supervisor, and he's actually in the audience. And it's on flavor and dark matter in a Scotto seesaw model. So if you want to check out the paper, it's already published in GHAB, and if you have any questions, feel free to interrupt me while I'm speaking. The motivation for this work stems from the fact that, as you know, the thermal particle physics is a very remarkable theory. It describes the fundamental particles and their interactions. It's very, very successful because it has made numerous predictions that have been confirmed experimentally over the years. You remember the discovery of the Higgs boson in 2012 by the ATLAS and CMS collaborations at the Large Hadron Collider, and it basically completed the standard model puzzle. However, we know from clear-cut experimental evidence that the standard model is incomplete and we need to move beyond it. For example, the baryon symmetry of the universe, it's observed that there's more matter than antimatter. And within the standard model, we cannot explain the observed value of the bow via the electroweak baryogenesis mechanism. Also, we have the evidence from neutrino flavor oscillations that neutrinos are actually massive particles and that there is lepton mixing. In the standard model, there's no right-handed neutrino counterparts, and therefore they are predicted to be massless and there's no lepton mixing. Additionally, from astrophysical evidence, we know that there is dark matter in the universe, and the thermal particle content has no viable dark matter candidate. So all of this points towards extensions of the standard model, where we add additional particles and/or symmetries that can be gauged or horizontal with the symmetries. So starting with the neutrino oscillation data, neutrinos can come from different sources, and there are different neutrino oscillation experiments that look, for example, that neutrinos that come from the sun, solar neutrinos, from cosmic rays, atmospheric neutrinos. The reactor neutrinos also accelerate the setups. And there's the transition probability of a neutrino that is produced at a source with a certain flavor alpha to arrive at a detector with another flavor beta. This is a quantum mechanical calculation. And as you can see, it depends on the neutrino mass square differences and also on the matrix elements of U. U is actually the lepton mixing matrix, which is parameterized in terms of three mixing angles, θ12, θ13, θ3, and the Dirac charge parity vacuum phase, also known as Dirac CP phase, delta. If the neutrinos are Majorana particles, we also have to take into account two additional Majorana phases. However, neutrino oscillation experiments are not sensitive to the Majorana character of the neutrinos. In our analysis, we used as best fit values for the low energy neutrino oscillation observables the ones that were obtained by global fits of neutrino oscillation data. Actually, we are using the best fit values from the domain. Basically, what they do is they perform a global data analysis of all neutrino oscillation experiments, accelerators and reactor experiments, and they obtain best fit values for the mixing angles, the Dirac CP vacuum phase, and also the neutrino mass square differences. So by looking at the data, we noticed that there are a few important things. First of all, is that the sign of the atmospheric neutrino mass square difference is not known, which leads to two possibilities for the neutrino mass ordering, normal ordering or inverted ordering. Additionally, if you look at the scale of these neutrino masses, they're about 10 to the minus 5 eV squared. So you can say that neutrino masses are about 0.1 eV, but actually we don't know what is the absolute neutrino mass scale. We just know that they are very, very tiny. And from the theoretical viewpoint, to explain why neutrino masses are so tiny, they're about 6 orders of magnitude times smaller than the mass of the electron, which is the lightest fermion of the standard model. This is still an open problem here from the theory viewpoint. Additionally, we don't have confirmation that CP is violated in the lattice sector. If you look at the delta phase for normal ordering, it's still compatible with the no leptonic CP violating scenario, delta equals pi or 180 degrees. Additionally, we don't know what is the octant for the delta to 3 angle. It can be in the first or the second octant. And from a theory viewpoint, the explanation of the neutrino masses, the nature of the neutrinos, the Dirac or Majorana, is still open question, and how to explain and reproduce these lepton mixing patterns. So in a model I'm going to show you next, basically we're going to answer a few of these questions in our frame. So the evidence for dark matter stems from astrophysics, named the most famous one probably is the galactic rotation curves, but also from the analysis of the anisotropies in the cosmic microwave background, Big Bang nucleosynthesis, and they reached the conclusion that about 27% of the total matter in the universe is dark matter, while the ordinary matter, the baryonic matter from which we are made of, only accounts for about 45%. So here I show the 3 sigma interval for the relic density for cold dark matter, which is obtained by the Planck satellite data of 2018. And from all of this analysis and evidence, we know that dark matter has to have the following characteristics. It has to be cold, non-relativistic, electrically neutral, cannot interact with the photons, has to be non-baryonic, and has to be stable or extremely long-lived. In our work, we're going to follow what is known as the WIMP paradigm, the weakly interacting massive particle paradigm, where the cold relics are produced by the freeze-out mechanism. So you open your Kolbe-Turner and you can see this Boltzmann equation, where n psi is basically the abundance of our species. Let's say it's dark matter. The Boltzmann equation has 2 important characteristics in it. One that takes into account the expansion of the universe with the Hubble constant, the Hubble parameter, and also one that takes into account the annihilation and the interactions with the thermal bed. So it's basically, this is known as the thermally average annihilation cross section. So the dark matter particle annihilates into small particles. And at some point in the evolution of the universe, what happens is that this term here becomes smaller than the expansion, and therefore the relic, so the abundance of our dark matter, freezes out and becomes constant. So in a model that proposes a WIMP, we cannot have overabundant dark matter. So we cannot have more omega h squared for dark matter candidates. We can only have underabundance because they can have multiple sources that contribute to omega CDMH squared. For example, an action and a WIMP model. But in our framework, we're only going to have one WIMP, and therefore we're going to try actually to be in this 3 sigma. So I hope I convinced you that the sample needs to be extended to account for neutrino masses and mixing, as well as reproduce the observed value of the dark matter relic abundance. Of course, throughout the years, multiple models have been proposed to explain both of these individually or in combinations. For example, the most popular, probably the simplest extensional star model that accounts for neutrino masses and mixing is the type 2 seesaw model, where we only add a single Higgs multiplet, actually a Higgs triplet, to the thermal particle content. And through its couplings with the Higgs in the scale potential, which is symmetry protected, and the fact that it can be very, very massive, actually the triplet can have a very small pair. And since it couples directly in the Lagrangian to the lepton doublets, the smallness of the web allows for order 1 Mikov couplings. And therefore, we have a 3-level generation for neutrino masses, which is natural. Additionally, in 2006, Ernest Mach proposed what is known as the scotogenic model. So skotos means dark in Greek, and in fact, this model solves both of the problems at once, because neutrino masses are generated at one level with a loop that involves dark sector particles, namely an inert doublet and a Majorana fermion F. These particles are viable WIMP dark matter candidates because they are stabilized by a Z2 symmetry. And neutrino masses are generated at one loop, which is very elegant. When we think about loops, we always think about small quantities. And also the interaction between the Higgs doublets and the inner doublet, which is phi dagger at squared, is actually symmetry protected, so it can be naturally small also. Our proposal is basically to combine both of these mechanisms and generate the neutrino masses by this interplay of type 2 seesaw at 3 level and scotogenic at one loop. But we are going to embed this into a single discrete flavor symmetry with the objective of providing spontaneous CP violations, so common origin for the atomic CP violating effects found in the vacuum phase. Also reproduce the neutrino oscillation data with some predictions, thanks to the flavor symmetry, and also guarantee dark matter stability such that we have a viable WIMP dark matter candidates. So now let's look at the type 2 scotogenic model. Here's the particle content and the flavor symmetry we're working with. So we extend the standard model with an addition of a Mariner fermion F, a Higgs triplet delta, complex scale sigma, and two inert doublets, eta 1 and eta 2. The flavor symmetry we are working with is the Z8 symmetry. Note there are three possible charge assignments, which depends on the charges we give to the standard model latent fields. We can have mu, eta, or meta. The role of the Z8 symmetry is crucial, first of all, because it allows to have low energy predictions. The idea is that the Z8 symmetry will restrict the number of couplings in the Lagrangian, and therefore we are going to have tight predictions, namely in the neutrino sector. Additionally, we are going to impose CP at the Lagrangian level, which means that all the couplings in the Lagrangian scale potential will be real. And the sole source of CP violation will come from the complex value of the sigma. And the Z8 symmetry allows us to charge the signal with omega squared. We're going to see that this is necessary in order to have a CP violating vacuum. Additionally, the Z8 discrete symmetry is the simplest non-trivial Zn symmetry that also have very interesting further predictions, but at the same time, when it will be spontaneously broken, since we charge the fermion F and the two inert doublets with odd charges, they will actually be stable under random Z2 symmetry. Looking now at the scalar potential and showing how this is possible, with omega squared, the following term, sigma to the fourth in the scalar potential, is allowed by the symmetry. We also add the soft breaking term, sigma squared. It's the only soft breaking term we add in the model. When we solve the minimization equations, we actually reach the conclusion that the theta phase from the vacuum is actually arbitrary, and its spontaneous CP violation violates CP. Now consider that our soft breaking term is actually zero. We don't add it. We still have a CP violating vacuum, but the theta phase is restricted to the odd multiples of pi over 4. So pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4. The problem is that for these very strict values, we fail at having compatibility with neutrino oscillation data. So we actually need the theta to move away from these exact spontaneous CP violating solutions. Additionally, the soft-breaking term avoids the cosmological domain problem. So now let's focus on the even sector of our scalar potential that is composed of the Higgs triplet, the Higgs doublet, and the Higgs singlet, the complex scale singlet. The Higgs triplet will couple to the Higgs doublet by this term in the scalar potential, and it is symmetry protected a la tau. That means it can be naturally small, and if it's zero, we gain an actual extra symmetry of the type of U1 both. The thing that's interesting is when we compute its VEV, it's proportional to this naturally small parameter, but also inversely proportional to the mass of the degrees of freedom of the Higgs triplet. So for a very heavy Higgs triplet, and the fact that this can be naturally small, we can accommodate VEV, for example, at the order of 1 eV, leading to sizable couplings in the Lagrangian with the latent doublets from the standard model. What we are going to consider is that the Higgs triplet degree of freedom actually decoupled from the remaining neutral even scalars, and therefore we are going to focus on the mixing between the Higgs, the CP even components, and the components from the scalar sigma, which will give three massive neutral scalars, H1, H2, and H3, with H1 being identified as the standard model like Higgs with mass around 135 GeV. For the dark sector of our model, we have two inert doublets. And the interesting thing here is that the inert doublets mix, and therefore the charged components of the inert doublets will lead to two massive dark charge scalars, and this will be very relevant for charge latent field violation, as we will see later on. Additionally, since we have two inert doublets, we're going to have four massive dark neutral scalars. And this will be very relevant for neutrino mass generation because they enter those photogenic loops, but also for dark matter. Because if S1 is the lightest dark matter particle, dark particle, it can actually be a viable range scale dark matter, which is also a thing that we're going to analyze later on. Focusing now on how neutrino masses are actually generated. So from the Yukawa Lagrangian, you notice that we have the following term here with the delta and the two latent doublets. This generates neutrino mass at 3 level via the type 2 seesaw mechanism. And the following terms here, that is the interaction with the Mariner fermion F, the inert doublets at the E, and the latent doublet L. The epsilon Fe Yukawa matrices are important, you'll see now. They will generate via these photogenic loops neutrino masses also. An important feature of this model is that the Mariner mass term for the fermion F is actually dynamically generated. It's not a bare mass term. It couples directly to the sigma, that acquires a complex set. This will have some implications later on for that matter. So actually, this model for the charge-dependent sector leads to a diagonal texture matrix. Therefore, all the compatibility neutrino data, the mixing, the connectivity violation comes exclusively from the neutrino sector. And for example, taking the Z8 in charge assignment, you notice that the Z8 symmetry leads to very few couplings in Yukawa Lagrangian. First of all, each Yukawa coupling, epsilon F1 and epsilon F2, only has one Yukawa, and those Yukawas are not overlapping. From the type 2 seesaw sector, we only have two Yukawa couplings with a very structure that has lots of zeros. And then, since we impose CP, all the parameters are real. So the only complex parameter is the vacuum phase. Once we compute the effective light neutrino mass matrix, we can see that the interplay between the two mechanisms, the scotogenic and the type 2, is crucial for the fact that the phase from the vacuum cannot be retraced away. So actually, we have a common origin for electronic CP biting effects stemming from the vacuum phase. No. So now we have basically what is the model, what is the idea, and we have some very interesting textures for the neutrino sector. Let's analyze its predictions. So how do we do this? Well, we have the high energy parameter matrix I just showed you. It has a two texture zero form, and it has to be matched with the low energy matrix, which is written basically in terms of the neutrino oscillation observables, the mixing angles contained in the mixing matrix, and the light neutrino masses. By performing this matching, we can test these zeros, which leads to low energy constraints. And for the different cases, I show here the textures for the IMU, ITAU, and IMU-TAU case. We updated the analysis that was done in this paper for our case for these three textures. And this will lead to predictions besides, for example, the Dirac CP phase delta, the Majorana phases, and also the theta-to-3 angle. It will lead to predictions for the light neutrino mass and also the effective Majorana mass. So this term is relevant for what is known as the neutrino double beta decay process, which basically infers on the nature of neutrinos in their Majorana or derived particles. So starting with the A1 case, it has texture zeros in the 1,1 and 1,2 entry. The predictions for the delta and theta-to-3 angles are shown in this plot. Note that for all plots, I will show the 1 sigma, 2 sigma, and 3 sigma data compatibility via these gray, blue, and pink regions. For the A1 case, the theta-to-3 angle is predicted to be in the second octant at the 2 sigma level, so in the blue region, while the delta phase is predicted to be between 0.8 and 1.6 pi at the 3 sigma level. The predictions for lightest neutrino masses are quite interesting because we have an upper and a lower limit at the 3 sigma level between 4 and 9 MeV. I indicate here the bound on the absolute neutrino mass scale from Catherine around 0.8 eV, and also the most conservative and less conservative bounds from cosmology on the sum of the light neutrino masses by Planck. You notice that for the A1 case, the lightest neutrino masses is well below the cosmology and Catherine bound. And also the interesting thing of this nature is has a zero entry. In the first entry predicts basically Majorana mass term, effective Majorana mass term equals to 0. That leads to a vanishing neutrinos of a decay rate. And therefore, this scenario cannot be probed by these future neutrinos of a decay experiments. Now let's look at the B3 and B4 cases, which have very similar predictions. And therefore, we are going to analyze them in some details. So first of all, starting with the delta and theta-to-3 angles, notice that for normal ordering neutrino masses, the B3 selects the first octant for theta-3 angle, while the B4 selects the second one. And when we go to inverted ordering neutrino masses, the picture is like inverted. We have B4 that selects the first octant and B3 selects the second octant. The striking prediction here, thanks to the Z8 flavor symmetry that imposes the two texture zero patterns, is that the delta phase is predicted to be at maximum 3 pi over 2. Looking at the light neutrino masses, notice that for all of the cases, they are now being probed by cosmology. Some cases lead to a lower and upper bounds on M lightest at the 3 sigma to sigma level, but the important thing is that cosmology manages to probe these predictions. Looking now at the effective Majorana mass, you notice that the Kamlan-Zen current constraint disfavors strongly the B3 case, and also B4 at inverted ordering. So I wrote excludes here, but it's not very true because we have also the nuclear matrix elements that leads to some uncertainty in the determination of the bound from Cameron Z. But okay, the case before normal ordering actually evades the worst possible constraint from Cameron, but it will definitely be probed by future neutrinos of decay experiments. So we see that the simple Z8 symmetry and the CP symmetry imposes basically very tight predictions for the neutrino set. What about the flavor? So the flavor, when I say flavor, I'm talking about charge latent flavor violation. So these are all these processes that are shown in this table. I present the current limits and the future sensitivities. Basically, you have the radiative process of one lepton going to another lepton with a different flavor and a photon in the end. You have the three-body case and also the Newey conversion in nuclei. Here I show the aluminium, titanium, gold, and nuclei. The most stringent constraints all come from mu1 charge latent flavor violation, which are highlighted here, which actually we are going to focus mainly on these ones in this talk. So in our sector, in our model, we have two different sectors, the triplet sector and the inert sector. And both will contribute in different ways to charge latent flavor violation. If you look at the Higgs triplets contributions, starting with the L alpha 12 beta gamma, these are all mediated at one loop level with the charge scale degree of freedom coming from the triplet and the double charge scale. The branching ratio of this process is basically proportional to the off-diagonal matrix elements of epsilon delta diagonal n squared. For the three-body decay, it's actually mediated at three level by the double charge scale. And it's proportional to the matrix elements of epsilon delta. The interesting thing of the Z8 symmetry is that it imposes that epsilon delta diagonal is diagonal for all symmetry cases. Therefore, the triplet contribution for the branching ratio of alpha 12 beta gamma is actually vanishing. It doesn't contribute. Whereas for the matrix elements of epsilon delta, since we have only two local couplings, and actually none of them have a common index, we cannot have processes such as L alpha to 3L beta, nor Newey conversion. So the number of processes our Z8 symmetry allows stemming from the Higgs triplet are only two. Tau to mu plus E minus, and tau to E plus mu minus. And here are the expressions for the matching ratio of these processes. What we are going to do moving forward is that we are going to fix basically the delta plus mass to be very heavy, and the local couplings are actually fixed to the neutrino oscillation compatibility, they're around 0.1. And so these bounds are easily evaded. These are the bounds that come from Bell experiment. Looking now at the inert doublet sector, they will mediate all the process radiating, namely for the L alpha, L beta gamma, and also the three-body decay, and also Newey convergence, all radiated, and it comes from the charge scalars. We have two, S1 and S2, which is crucial because since we only have two Yukawa couplings, which are not overlapping in Yukawa matrices in the weak bases, once we go to the mass spaces, since the inert doublets mix, we're going to have a mixing angle. So we're going to have effective Yukawa matrices where we have two couplings. And this allows us basically to have processes that violate flavor. If these things didn't mix, basically if the inert doublets are not mixed, all predictions for charge latent flavor violation from the inert doublets are basically there's not, they're all zero. But in this case, they do mix, so we're going to have the only predictions are for each Z8 alpha beta case. We're going to have L alpha to 3L beta, L alpha to L beta gamma, and also the Newey conversion case is only viable for Z18. So overall, the contributions stemming from the Higgs triplet and the scotogenic sector for charge latent flavor violation are not overlapping. And this leads to interesting falsifiability for our model. Because, for example, if we measure two radiative processes, basically our model is excluded. If we measure, for example, this tau decay and the tau to 3 nu, our model is also excluded. Because for each charge assignment, only very few non-overlapping processes are allowed. So we are going to focus on the Z8 in nu case, because it leads to the mu1 charge latent flavor violation I showed earlier at the most stringent bounds. But how are we going to implement this and perform our numerical analysis? Well, what do? We use common packages that used by people in the papers, namely SAR for model implementation. It's a mathematical package. You put in the Lagrange and you put in the particles and the parameters, and it generates the steering files that enters other packages like Espino and flavor kits that basically calculate the masses, the mixing, the branching ratio, the conversion rates for all our favorable phenomenology. But also it generates calc-head files that links directly to micrometers, the package that calculates basically the Rayleigh density, the direct detection, which will be used in our dark matter analysis later on. To run all of this, we use SSV, which links all the packages and performs the numerical scans. We're going to vary the parameters that are present in our Lagrangian and our scale potential. The following way, we are going to focus mainly on the nut sector, and this is the fermion mass that is dark. All the points with respect to perturbativity coupling to be at 1. We are considered that the Higgs triplet is decoupled and does not mix with the remaining scalars. All points respect the compatibility with neutrino oscillation data through the parameter reconstruction, so the couplings are fixed to the best fit values for neutrino oscillation observables. We focus on the Z8 immune normal ordering case because it has the most stringent muon charge validation. So here I present tutorial plots. Basically, it's the branching ratio of mu gamma in terms of branching ratio of 3E and all the conversion rates in aluminium, titanium, gold, and lead. I indicate the current balance via these vertical and horizontal green lines, and the projected sensitivities via these dashed red lines. So first of all, just by taking a glance at these plots, you notice that there's a large chunk of parameter space that's actually already excluded by the current experiments, but also the remaining one will clearly be probed considerably by the future experiments. To name a few experiments like MEG2 and MEG are the experiments that look for mu gamma. However, as you can see, there's a tight, it seems like there's a linear relation between the branching ratio mu gamma and the remaining ones. And this has to do with the dipole dominance factor in our model. But there's still a tight spread. And this spread can be explained if you look directly at the formula, for example, for the branching ratio mu gamma. As I mentioned, it depends on the two dark charge scales in our model, and therefore their masses enter this expression. So the spread can be attributed to the fact that the masses are not always the same. In fact, if the masses are degenerate, the branching ratio is 0. If the two inner doubles do not mix, the branching ratio is also 0. It has a quadratic dependence on the product of the two Yukawa couplings we have in our model, as you can see in this plot. And it has an inverse dependence with the mass of the charge scale. So for very, very heavy charge scales, can be around 1 TeV, the branching ratio for mu gamma actually evades all the bounds. An important bound I show here is the exclusion by lab of the charge scale masses that has to be above 70 GeV. So now we have looked at the flavor predictions of our model. We are now poised to study its dark matter phenomenology. So we are going to continue to focus on the Z8 mu normal ordering case, since the dark matter results are not affected in a substantial way if we change symmetry cases. All the points I'm going to show you respect charge atom Verweiting bounds and are compatible with the neutrino oscillation data. Additionally, as I showed before, the Z8 symmetry, once it's spontaneously broken down, it leads to residual Z2 symmetry, where the Majorana fermion F and the inner doubles are odd. So we have two possibilities for weak dark matter, a scalar and also fermion. We are going to analyze both in one folds. The Rayleigh densities, the direct detections are all calculated with micrometers. So starting with the scalar dark matter case, we consider that S1, our dark neutral scalar, is the lightest dark matter particle. And here I present the Rayleigh density in terms of the dark matter mass. Note that the black points are the ones that reproduce the absolute value of the Rayleigh density by Planck at the 3 sigma level. The orange points are overabundant, while the gray points are basically underabundant. I show here a bound by lab, which is not the same one as the charged scalar mass, but it's a bound that comes from the fact that the Z boson decay loop has been very tightly measured. And since we have inert doublets, they have hypercharge and they have non-trivial representation and SU2L, basically what happens is that the neutral components will couple to the Z boson, and the Z boson cannot decay into these dark matter particles. So their masses have to be above 45.6 GeV, which basically excludes all of this blue shaded region. I also mentioned here some dips in Rayleigh density, which can be understood by looking at the annihilation diagrams of dark matter into small particles. The first dips, which are actually two, occur when the annihilation diagrams are mediated in the S channel by the W and the Z boson. So basically, these dips occur at half of the mass of W boson and half of the mass of the Z boson. The second dip, which is much more efficient, it has to do with the S-channel mediated Higgs diagrams. It's more efficient because in these cases we have momentum suppression, and here we don't. It's so efficient that there is no viable relic density points between 61 and 90 GeV, 61 and 68 GeV. This third dip occurs when the quartic interaction with the two dark matter particles and the gauge bosons is possible. It occurs at around the mass of the doubling Z boson. The fourth dip occurs at the mass of the Higgs boson by the quartic interaction between dark matter particles and the Higgs. And the fifth dip has to do with the fact that we can have scattering into final state top quarks. An interesting feature of this model is that we do not obtain the correct relic density for these high region masses above 500 GeV. This is interesting because in usual Scotto seesaw setups, where we only have one inner doublet or in the inert doublet model, we obtain the correct relic density for masses above 500 GeV. The reason for this is that at some point the relic density always depends on 1 over the dark matter mass squared. But when they become very massive, the thermally average cross-section dips, and when it dips, the value of the relic density, since it's inversely proportional to scattering cross-section, it goes up, and we recover the correct relic density value. For our case, this does not happen because we have 2 inert doublets. So we have 4 neutral dark scalars that can co-annihilate via co-annihilation diagrams. We also have the charge scalars that leads to additional co-annihilation diagrams, and we also have the Mariner Fermi. So all of these co-annihilation diagrams will contribute to the thermally average cross-section, and therefore the relic density would still be very low, up to 1 TeV. So the 2 regions that are compatible, in summary, are basically from 45 GeV to 61 GeV, and 68 GeV to 90 GeV. How can we constrain even more this very tight variable parameter space? Well, there's these 2 diagrams that occur at 3 level in our model, where you have the dark matter particles that basically, via the Higgs interaction, can interact with quarks that can be in a nuclei, and the same occurs by the Z boson mediation. As I mentioned before, this diagram is the most dominant one because we still have momentum suppression here. This will actually contribute to what is known as the WIMP nucleon spin-independent elastic cross-section that is constrained by WIMP dark matter direct detection experiments. So here I show the plot of the sigma SE in terms of the dark matter mass. I have the left bound, and I still maintain the same color code for the relic density abundance. The black points are the ones that are viable. Here I show all the direct detection experimental constraints on sigma SE. I actually put an update on this plot that is not in the paper because there was a recent results, the first results by the LUXEP in collaboration on sigma SE, which actually currently is the most stringent bound on sigma SE. And as you can see with this update, the region between 45.6 and 61 GeV is actually excluded by the direct detection experiments. While there are still some remaining points in the region between 68 and 90 GeV, but they will be definitely probed by future experiments, such as the future projected sensitivity from the LUXEP experiment, which is actually the same as the xenon and TON. And these dark matter direct detection experiments, they can only reach and probe and constrain this parameter space up to the neutrino floor that comes from coherent elastic neutrino scattering. But okay, you have to take this bound with a grain of salt because it depends on the fluxes of the neutrinos, which have a large uncertainty. So this contour here can be a bit lower. It depends. So, but this is not the end of the story because we can still constrain this parameter space via what is known as LHC Higgs boson data. Because we have dark matter scalars that interact with the Higgs boson, the Higgs boson can decay into them. And this will contribute to the branching ratio of Higgs to invisible. You can ask the question of why the Higgs does not decay into the charge scalars. So, well, it cannot because we have the left bound that constrains the charge scalar masses to be above 70 GeV. And this decay is only possible for masses of the dark neutral scalars to be below 62.5 GeV, as you can see in this plot. So the exclusion provided by the LHC is indicated in this blue shaded region. And actually, it tightly constrains the mass region between 45.6 GeV and 61. But in combination with the Higgs to diphoton rate, in our model, we have dark charge scalars, and therefore, through these one-loop diagrams, we can have contributions to the heat to photon-photon. And the constraints from the LHC are shown in this dark shaded, blue shaded region. And if combination with the Higgs invisible decay and combination with the direct detection of data results basically excludes the mass region between 45.6 GeV and 69. The only viable region in our model for successful reproduction of the valid density by the scalar dark matter candidate is the one between 68 and 90 GeV. So now let's turn our attention for the fermion dark matter case. So for the fermion case, I show here the relic density in terms of its mass. Notice that we recover the same dips in relic density. Basically, the first two dips are mediated by the S channel of boson, S channels at boson, and the third dip is S channel Higgs. So apparently, for the fermion case, the allowed mass region is above 45 GeV. But in order to understand this, it's crucial because if you only have annihilation diagrams for the fermion, you actually don't recover the correct amount of relic density because it's always overabundant. But since we have co-annihilation possibilities in the model, by all of these diagrams, we can obtain the correct value of relic density. In order to confirm this, we basically plotted the relic density in terms of the mass splittings between the fermion and the dark matter scalars, and also the fermion and the charge scalars. And we showed that for mass splittings below 10%, where the co-annihilation channels are relevant, we always recover correct relic density values. Another interesting possibility or scenario is the fact that we are going to have a possibility to constrain our model for the fermion dark matter case by direct detection. This usually doesn't happen because Mariner fermion dark matter models, they usually have a bare mass term. So if you have a bare mass term, there's no three-level contribution to the spin independent elastic cross section. And also it can be shown that for Majorana type fermions, there's actually no one loop contribution also. But in our model, since our mass of the F is dynamically generated and the sigma scaling mixes with the Higgs doublet, we have the possibility of having this diagram at three levels. And of course, this diagram will depend strongly on the mixing angle between the Higgs doublet, degrees of freedom, and the scalar singlet. Here in this plot, we consider that the third H3 scalar actually is very, very massive. And therefore, the mixing, the substantial mixing will be between the CP even component of the Higgs boson and the CP even component of the scalar singlet. So we have only one mixing angle. And if we plot the sigma SE in terms of the mass of the fermion for the different values of this mixing angle, this is the upper bound on mixing angle from colliders. And from the mixing, we notice that if we are at the upper bound, actually the model is excluded by direct detection constraints. But if we lower the mixing, which can be done by having high VEV of the scalar singlet, so high mass, or basically by having a very small coupling between the Higgs doublet and the sigma that comes from the coupling phi dagger phi model sigma squared in the scalar potential, we can lower this mixing. And for values below 10 to the minus 2, we are below the xenon 1T bound, and for values below 10 to the minus 3, 10 to the minus 5, we actually are below the neutrino floor. So to briefly conclude, I showed the model where the neutrino masses are generated by an interplay of the type 2 seesaw mechanism at tree level and the scotogenic loop. We embed this into a Z8 symmetry that is spontaneously broken down into a Z2 symmetry that stabilizes our scalar and fermion dark matter. The Z8 symmetry leads to very tight constraints in the neutrino sector because we have a two vector zero pattern for the mass matrices. Additionally, we have CP, so we have a common origin for leptonic CP biotin effects. The results for the bit3 and bit4 case is that one of the delta 2-3 options is selected, and the delta phase is predicted to be at maximal CP violation 3/2. The predictions for the lattice neutrino masses are basically being probed by cosmology, while the predictions for the effective Majorana mass will be probed by future neutrinos of beta decay experiments. We analyzed the flavor implications of our model in Charles-Lepton flavor violation. We showed that a large chunk of parameter space is already excluded by the current constraints, and the remaining one will be probed by future experiments. It all relies on an interplay of the mixing of the inner doublets and the charge scalar masses, and the Ducal couplings, which are only two. We analyze the dark matter phenomenology, where we have a scalar dark matter, taking into consideration all the constraints from direct detection experiments, from Higgs, LHC, Higgs boson data, we arrive at the conclusion that only the 68 GeV to 90 GeV mass range for the scale dark matter leads to correct relative density. And as for the fermi-aquatic case, we showed that for masses above 45 GeV, we always recover the correct relative density because we take into consideration co-annihilation channels. So thank you very much for listening.
Many thanks, Henrique, for your very nice and interesting seminar. So now we have space for questions. So you can just raise your hand and ask directly to Henrique.
So I have two questions. I'll ask one and then I'll let you. So the first one is, you have a very strong coupling in the case of the scalar normal, you have a very strong coupling with the Z boson. You said that why you got the lead bound, a hard lead bound. But you have such a strong coupling to the Z boson that your dark matter can annihilate efficiently to Z boson and to, for example, neutrinos.
Yes.
And or gamma rays. So have you considered constraint from indirect detection through gamma rays, neutrinos, even potentially antiprotons?
No, we did not consider that. Aren't these constraints more for lower mass regions?
Well, not necessarily. You can have, especially if the annihilation is efficient.
It can be okay. No, we have not considered, just put the hard lead bound on the thing. But that would be interesting.
Especially since you probably know that there's a future mission called CTA, which will, for like intermediate range masses, will actually be probably very good to control.
Okay, I can look at it. Thank you. Let's see. Please.
So you mentioned that you had a CP validating solution of the minimization condition, but I wonder, do you also have CP conserving solutions?
Yes, of course. Yeah, when you do the minimization conditions, you actually arrive at three possibilities. One where the theta phase is pi, so that's completely non-CP. Then there's a solution with pi over 2, but actually can be shown by rephasings that the scale potential is CP conserving. Actually, it's not a CP validating solution. And then you have the solution which I showed, which is the only spontaneous CP validating solution. That is actually the exact Z symmetric limit. It's pi over 4, but if you have the soft breaking, it can be whatever you want.
And it tells you the global minimum.
Yes, the global minimum constraints, these are parish. Wait, there. It depends on the coupling, basically. Okay, so the global minimum condition depends on the quartic coupling there and the soft breaking also. But I should have put it here, but it is. You have to guarantee some relation. We guarantee that in numerical perspective.
And sigma is the triplet.
No, sigma is the single. The triplet is delta. So, yeah, the triplet is delta. So the scalar singlet is sigma. Yeah. So yeah, for the triplet you need more CP validating terms, which we don't have actually. The CP that are phase dependent are exclusively from the convex system. So it's the only possible solution to have actually spontaneous CP validation. So we analyzed everything and we saw this has to be CP conserved and this has to be CP conserved. These are inert because for that much stability, and this is the only possible.
Other questions? We have already a question already good. So you can go ahead.
I couldn't see from the plot what is the cosmological bound that you use for the sum of neutrino masses.
Oh, we actually put the two bounds.
There are two bounds there that we have.
Okay. Okay, there's two bounds. That one that's only basically there's the 0.12, which is this one, which is has everything balancing the parametric oscillations, and then there's the less conservative, which is on 0.54, and the sum of the neutrino match. So we actually showed both. Because why did we show both? Because it's come from an indirect astrophysical measurement, while the cutting is a direct bound. So okay, it has to be taken with the grain of salt.
Yeah, especially that was exactly my comment. The VO, especially VO constraints, a bit flimsy, so that you can shift a few more up, a few more down.
Yes, that's why you cannot say if you have something here that is excluded. You can only say it's being probed.
Yeah, absolutely, absolutely.
And also because actually the region which is being probed by the model is exactly in that band in the uncertainty of the boundary cosmological sum. So that's why it's imperative to show both bounds.
Yeah, exactly.
To show,
Yeah.
as you can see there, exactly.
Yeah.
Yes. So I had another question regarding CP violation. So now if you have CP violation in your model,
Yes.
wouldn't you also get phenomena like electric dipole moments of
Like for example, T minus.
the electron? Well, that's not super likely. But electric dipole moment of the
EVS,
electron,
yeah, we haven't checked that actually, but perhaps we have.
and also your scalars, we have mixing between the
Yes, we have
CP also,
here. CP even CP.
but also for the not doublets.
Yeah, for the another we. Sorry. Because I don't know why it doesn't skip to the next. Yeah, of course, you have the mixing with every.
Oh, okay.
CP
sorry,
and
I
CP
missed
out
it.
component.
Yes.
Yeah.
Thanks.
It's actually crucial for the neutrino mass generation. That's the this type. And this one is crucial for having traveling or else we could.
So for actually, for the electrochemical moments, so your calculations, are they real or
They are real because we impose CP conservation.
so you don't have electrochemical moments?
That we can have
You
with
have
spontaneity
CP on the scale.
in this case.
And how can you use it?
But
There is mixing scale to the scale.
okay. So I haven't checked that.
But I have another question after that. So you have the lightest neutrino mass, but what is the heaviest neutrino mass?
Oh, well, it depends on the case. First of all, for example, for the A4 case, there's actually a lower and upper bound at the 3 sigma level. So it's between 4 and 9 10 to the minus 3 eV. So it's well below the Catherine, you see at 0.8 eV. For the remaining cases, some do not have an upper bound. We always have a lower limit, that's for sure.
No, but Antonio is not asking that. Antonio is asking, you have that lightest neutrino mass.
Yes.
What is the mass of the heaviest?
Oh, okay. I thought. Okay, sorry. I thought it was
The
upper
mass of the
Oh, I haven't put it in the plots, but
That's fixed by the delta square.
Yeah, that's the
Once you
thing,
know
yes.
Once you know the mass of the lightest, you just have to add the delta square.
I actually put them here.
Do you take the mass splittings with using a range as well? So that's with the
These ones. And for normal ordering, the heaviest is M3, so you just vary its mass. You have your lightest and vary the mass of the 2 signals you get in the center. Inverted ordering actually is the opposite. So M1 is the heaviest, M3 is the lightest. M2 is the heaviest, M3 is the lightest.
Yeah, so for the analysis of the lightest neutrino mass, actually the fit is done, it's a global fit. So we considered already the chi-square profiles for the neutrino oscillation parameters. So it's for the rest of the analysis, the charge left and further, we just take the best fit points because they will not change the results much.
More questions?
So you already mentioned this, so that's why I'm bringing it up. G minus 2.
Actually, I think
But you have already need to gamma, which gamma is so
Yes,
in that process.
I think it wasn't possible because it's always negative. Parameters
okay,
which we are
It's too small.
Yeah, it's too small for sure, because otherwise you will have to match.
yeah, but yes.
This is not a usual 2 Higgs-level model where you can play with tangent beta and
There's no
enhance the
Yeah.
More questions? That's. I actually have one or two, but I mean, it's from a different perspective. So, to be a dark matter candidate, you need to satisfy some of the current open problem. So, for instance, some of the WIMPs actually do not solve the cusp core problem or the missing satellite ones. So my question would be, is this model able to solve the dark matter problem that we are searching for?
From the cosmological side of things,
Yes.
yeah, I cannot answer, honestly. Cannot. We just do it in particle physics perspective. So can you get dark density? Okay. Can you get constraints from dark detection? I cannot answer that.
And the second part is actually related to that, but you can also not answer, it's fine. Is that taking your Lagrangian, it's always something that you didn't search because clearly you're doing another kind of work, but can you actually produce objects, macroscopical objects? Or have you thought about how can I place these in Einstein equation, trying to see if I get a dark matter halo?
No, we haven't thought about it. But that would be interesting, like perhaps linking it to inflation, that would be interesting. Also. One of the skills can be input. These type of things can be seen, but we haven't not looked at that at all. So it might be interesting.
So what is the mass of dark matter here?
So we are putting it between 10 and 1 TeV.
Okay, so it would be microscopic object.
No, but it will form eventually, it will form halos in the
Yeah.
same way that any wave does. So I don't think there's any difference from the traditional dark structure formation from halos, from WIMPs.
So where you still have the problems of WIMPs.
Exactly, you still have the same problem with WIMPs. It's the same range of like traditional WIMPs, just it comes from a different source.
More from the dark side out there? Okay, I think a round of applause for Henrique. Thank you.